30, let's say 35 bases, which is the one end of these fragments that we made previously. You will have to photograph this entire flow cell in this high resolution 35 times. And if you do what they usually do now, you do so-called paired reads. So you take both ends of this fragment. You have to do it 70 times. And each machine per run produces 4 terabytes of image data. And this is already LZV compressed. Then computers run over this and try to piece together from these little gray dots that you saw on the previous slide what that means. So they have color filters there, and it's actually 4 colors, and you get 4 images for each possible base. And the output that I see, so I'm not working with the sequencing machines themselves, I work with the primary output, which is long lists of these data sets. So these 4 lines represent one of these fragments that were amplified and then sequenced. So this is an individual name. This is, I think, 37 bases from one end. This is 37 bases from the other end. And there are, in this case, I think, about 200 bases missing. It's not that I cut them off because they don't fit on the slide. I don't have that data. This data is lost. So you only know the ends of these fragments, but not what's in between. And then you have here a quality score, which is ASCII encoded, which basically says, oh, the machine was as a certain quality score of how sure the machine is that this is really an A in this case, which is, believe me, not a reliable metric, so it's best guess. So you get lots and lots of lines of this. So each flow cell has 8 lanes, which run in parallel and can carry different samples to be sequenced. And at the moment, I get per lane, I get about 9 million of these. So it's quite a bag of reads. And this is what they look like in a so-called alignment. So as you can see, the bases in one column are always the same. It's a little hard to see probably. So everything here is a G, and these reads are aligned because there are multiple sequencing strands of the same original molecule. So this base here, for example, has been sequenced, I don't know, 20, 30 times in this process. This is the same view, a little more condensed, so there's a little more data on here. And maybe you can see this, the ends are in blue, and in gray is a missing part. So basically, down here, imagine this is your DNA, your chromosome, and it goes along here, and this is where these reads fit. They were fitted to a reference sequence, and the blue means they are a perfect match, and the red means they are not matching the reference sequence at that point, but it's the best match that could be found. So when you see the red here is clustering at this position, then you can assume very safely from that this base in this sample is different than the one that was used as a reference. So you might say, okay, it's a new sequencing technology, so what, who cares? there's a website, a database on the internet called GeneBank that contains all the sequences of all the organisms that were ever sequenced in the last 35 years. So there's human, there's mouse, there's some fish, there's bacteria, there's yeast, there's everything. They were all sequenced with the old technology. And this amounts to 200 gigabases or billion bases that are in this database. This is the entire sum of human knowledge about sequences in organisms. The Sanger Center, which I showed you in the beginning, trialed a few of these Solexa machines at the end of last year, and they started basically production in January. And in the first 3 months, they produced more than that. In 3 months, they produced more sequencing data than the entire world in 35 years, using 28 machines and 20 people to run them. And as I said, Sanger trialed these machines end of 2007. So when they started in 2008, it was still rather experimental process. I was still learning how to use them correctly, what parameters to set to get the maximum output. And of course, they improved on this, and each machine is churning out 20 gigabases per run now, which is 75 terabases or 7.5 terabases or 7,500 gigabases per year. Is the current output is actually a little more like 9 terabases at the moment, because this was written last month. So you can see how this is changing, and it is changing, and whole new modes are becoming available right now. So they're increasing the read lengths now from 35 or 37 to 50. I've seen 50, works very well. There are apparently trials with 76 and even 100, which would put this in the same ballpark as the original Sanger sequencing, which made one of these reads per run, and this does like 9 million per run. This 7.5 terabases will at least double next year. It will probably be more. How am I doing? Oh, okay. So this is not just, it's a new technology that works a little better. This is a whole paradigm shift in this area of science, and it has great potential, but it poses great problems, because until beginning of this year, scientists kept running around, so biologists, medical people kept running around. Oh, I need my favorite gene sequenced now. Why do I have to wait so long? And this year, and I've repeatedly heard people say that, here's your gene sequence. Oh, we didn't sequence it once, we sequenced it 20 times because we had spare capacity. And I said, what am I supposed to do with all this? It's a real problem, because there's no algorithm, there's no software, there's no concept of how to deal with this, with all this data, because for the last few decades, everything that was developed on the principle, we have a sequence, now we have 20 people who can look at this single sequence. And now people are drowning in data, and they don't know what to do with it. Problem gets worse if you realize this, we let the computer puzzle it together to one sequence. It doesn't work. what you get is you have software that can puzzle these things together to long pieces, 10,000, 50,000, 100,000 bases, but that's the end of it, because some parts in natural DNA, in our DNA, in every organism's DNA, has certain structures like repeats, so it goes on 80, 80, 80 for thousands of bases, and unless you can sequence through this entire stretch and see both ends of this repeat sequence, you don't know how long it is, and you have no way of finding out how long it is. And so every time this occurs, you need some human to make a guess and puzzle it together. Well, let's say you can puzzle it together. You have a new genome now of some species you have no knowledge about otherwise in terms of sequence. This stuff needs to be annotated. It's just a bunch of very long strings, and no one knows what they mean. So you have to go in there and mark up, oh, this is a gene. And it's not as trivial as it sounds, because even today there is no good way for automated annotation for this stuff. If you let the best software run over a human genome today, you'll get probably 50% false positives and 50% of the genes that it misses. So automatic annotation is not the solution, at least not now. And you can only throw so many people at this because, again, people have to be trained for this. They have to know what they're doing to annotate this stuff. And I know some of these people, and they say, you can do this for 2, maximum 3 years, and after that you go crazy whenever you see a screen with all this DNA on it, because it just, you stare at this stuff 8 hours a day. And it's like a very complicated Tetris. And you can play this occasionally, but after 3 years of doing this every single day for 8 hours, you just run away screaming. Of course, I want to mention that other technology we use. So this is sequencing machines put out lots of data, and it's really lots, and it's getting more. As I said, they get more data from the machines, so it means more data is coming onto the servers. So currently we are generating about 300 terabytes per month, and that needs to be stored somewhere. We do have 3 petabytes in our farm at the moment, more or less. Even the systems people couldn't tell me how much exactly it is, because they're too busy adding new hard drives. This is all that some people do. They just plug in new hard drives until the rack is full. Actually, even with that, they are losing currently. So just beginning of December, basically last thing I heard was they locked down some of the user space on the hard disks because sequencing machines kept churning out new data. They didn't know where to put it. So I hope it didn't blow to, I don't know where, when I come back in January and find the thing has become a giant meltdown. Backup is a problem. They have robots. They have robots to store the stuff on tape. So the robots are just changing tapes, putting the tape in. It's written, taken out. It has automated IDs and barcodes on it and all kinds of things. This is running 24 hours a day. But they have a backlog of, I think, half a year right now, which is not backupped. There's a mirrored hard disk, probably in the same rack. uh,